All right, guys, we're back after lunch. Thank you all for coming. Now we've got Brett and Patrick talking about Dijkstra Maps and Roguelikes. So take it away.
Thank you, Kawa. Just going to make sure that I have control over the slides here. Because, yeah, the thumb drive guy just jumped up on the screen, so let me see. Hey, there we go. Okay, cool. So, yeah, the goal of this talk is not to get deeply technical into how to calculate Dijkstra maps and do all this grid-based pathfinding stuff, because there are plenty of tutorials out there if you want to learn how to do it. Basically, Patrick and I think, are just trying to show what they are, how they can be used, what interesting things you can do with them, and why they're cool. So we're not going to get deeply technical, and our intended audience is just about anybody who's interested in some of the technology or techniques behind pathfinding. So here we go. So first we'll just introduce ourselves. Yeah, so my name is Brett Gildersleeve, and I'm just a hobbyist developer. I've participated twice in 7-Day RL, and that's pretty much the entire body of my work as far as game development goes, but I had a lot of fun with those games, and I'm hoping to continue to participate and maybe get some LD48s under my belt moving forward here. And my recent games, my only games really, that I've made are Rogue Space Marine and Helix, and you can see some screenshots of those in the upper right corner. And this, should I just introduce you, Patrick? Sure. Okay, and this is Patrick Kenney, and Patrick has participated in several Ludum Dares and 7-Day Roguelikes. Two of his recent games are shown here. Psycho Tennis on the left, which won a gold medal in LD48 for fun, in the fun category. Very cool game. I strongly recommend that you check it out. And on the right is Billiard Dungeon, which was his most recent 7-Day Roguelike entry. And that game actually uses Dijkstra Maps to do some of the AI for the non-player characters. So he actually has practical experience with Dijkstra Maps, whereas for me it's just more of a fascination of mine. I haven't actually used them in a practical game yet. So we are standing on the shoulders of giants here and kind of borrowing ideas from those who came before us. Many ideas from this talk were taken from Brian Walker's article called The Incredible Power of Dijkstra Maps. So Brian Walker is the creator of Brogue. And a developer by the name of Derrick S. Creamer created this game called Forays into Nerendon, so you should check that out. And I contacted him to use a Dijkstra Map visualizer tool that he created when he read the aforementioned article from Brian Walker and was interested in creating some visualizers to kind of complement that article. And so all that stuff is up on Rogue Basin, and you should definitely check it out. And really, this presentation that we're giving is just kind of a distillation of content that's already actually out there and you can already find out in the world. So yeah, so the overview of just what we're going to be talking about today is just a very basic understanding of how grid-based navigation and pathfinding works, and kind of A-star, basic idea of how it's calculated, what makes it good, where it's not so great in certain applications, and then we'll move on to Dijkstra maps and sort of how they're calculated in a very hand-wavy way, and the advantages and disadvantages of Dijkstra maps, and then we'll just move on to interesting applications of Dijkstra maps and how you can use them in roguelikes in particular. And those kind of applications fall into a couple of different categories. Sometimes it's just a simple replacement for what you do with A-star. Sometimes it's something really cool that A-star either isn't capable of or it's not able to do in an efficient way. And also we'll just talk about some more experimental things that potentially could be done with Dijkstra maps. So just a really basic understanding of grid-based navigation. This is a problem that often needs to be solved in game development, and the problem is how do I get one actor from one point on this map to another point? And often you'll have areas that can be traversed, shown here in the white squares, and then areas that can't be traversed, shown in the blue squares. And if you were to kind of blindfold yourself and throw 2 darts at a dartboard, what's the most efficient path to get from one point to the other? And that's the problem that you're trying to solve with grid-based navigation and pathfinding. And one of the most common techniques for solving this problem is called A*. It's an algorithm for calculating that optimal path. And I'd recommend that if you don't know how A* works, watch this video series from Sebastian Legge. He's a South African game developer with a really great YouTube channel, and I contacted him about using a video, which I might be able to show on the screen, but probably don't need to. I'd say just go check out that video series if you're interested in how A* works. But the real key takeaway from A* is that it's a point-to-point solution. So just this example image on the bottom of the screen, you have an actor and a goal or a target, and each one of them is on a square somewhere in the map, and you need to calculate the most efficient path to get from one square to the other. And so this just shows a simple example path that was calculated by A*, shown in the black squares going around the obstacles, which are highlighted in red. And you're basically getting from the starting point to the ending point in the least number of moves. And that is the fundamental way that A* works. And it has its pros and its cons that I'm just going to outline here. One of the major key selling points of A* is just the fact that it's so ubiquitous. It's everywhere. There are so many different implementations that you can go find open source solutions to this online. And if you are just starting out making a game and you don't know how to get your NPCs to move from one place to the other, like I was about a year or two ago when I was making my first game, I just took an off-the-shelf A* implementation and I just plugged it in and it worked. So that's a great reason to use A*. It's relatively easy to implement just because there's so many tutorials out there that show you how to do it. And you can call it on demand. So basically when you need a path to get from one place to the other, you can call the A* algorithm to come in and do the work, generate a path for you. And when you don't need it, you don't have to call it. So there's no kind of performance overhead when you're not actually actively using pathfinding. And if the 2 points that you're trying to make a path between are relatively close, it's fairly efficient. So of course, the more complicated that the map gets and the farther away the 2 points get, and the more points there are on the grid, it gets there's an increasing cost in the processing for the calculation. So those are what I would say are the pros. The cons to this approach is that because it's a point-to-point path that you're generating, anytime an actor moves a square or something on the map changes, you might have to recalculate the path, which is expensive. So it's you can use it until something changes, and then you kind of need to recalculate. So that can be inefficient, and that is potentially a problem. And if there are many actors, let's say, for example, you have 50 NPCs that want to go attack the player, each one of them has to separately call A* to calculate its path to find its way to the player. And so now you have 50 calls to that function, which adds up, of course. So in turn-based games, it might not matter, but in real-time applications, this can be a tremendous performance sink. So that's potentially problematic. And so in real-time games, the solution can be to spread that calculation out over multiple frames. Yeah, and I guess this just kind of ties into what I said before, but you're only calculating a single path, so you're not able to calculate a map that, or something that covers the entire playing space, which is something that Dijkstra can do. So so now we're moving on to Dijkstra maps, and the way that Dijkstra maps differ from A* is that a Dijkstra map calculation is done over the entire map, or I mean sometimes a subset of the map, but for simplicity's sake, let's say the entire map. So in this image here, you see the @ symbol in the center representing the player, and this is a map that's calculated using the player as a target. So you could think of an example where an AI, an enemy, wants to find the shortest path to the player. And so the map is calculated for every node on the grid, and it's given a number. And that's usable by any actor within the grid. So just a simple example, if I had an actor that wanted to find a path to the player, shown where this circle is, starting on the number 9, all you do to navigate to the player is walk yourself down numerically until you get to the goal. So 9, 8, 7, 6, 5, 4, 3, 2, 1, and you're at the player. Depending on the way that you implement the movement, you might have this path, you might have this path. It's also perfectly good, 9, 8, 7, 6, 5, 4, descending, right? If there's no extra cost, moving diagonal, that works. This is even a valid path, because if you look at this, I mean, it doesn't look intuitively like the best way to get to the player, but you're still obeying the rules because you're stepping down one number at a time, right? So, but this is the basic gist of what Dijkstra maps are and how they can be used. So the pros to this is that you can generate one single map and multiple actors can use that. And any actor can make use of the map at the same time. The map can cover the full level. And those are all things that really A-star can't do. The cons is that the calculation is expensive relative to A-star because you're doing a calculation for the whole map. Whereas A-star, basically, it's processing up until it finds the solution and then it stops. So if you're lucky and you're doing a short path with A-star, it's a pretty quick calculation. And another con to Dijkstra maps is that, at least in my experience, it's kind of hard to find off-the-shelf implementations, and so you might find yourself coding up your own solution to this. I don't know if anyone has any good open source off-the-shelf implementations. I'd be happy to learn about those. So the example I showed previously, single actor, single goal. So the goal here is the player. I put an actor, which is a little green G, a goblin, down in the corner, and generate the Dijkstra map around the player, and that goblin can just walk itself down numerically until it gets to the player. So that's the simplest example. Now, when you stick in obstacles into the map, and I'm not going to go over how the map is actually calculated here because that's sort of outside of the scope of this talk, but we've now moved the player up into the corner and the goblin down into the lower left corner and put a bunch of walls blocking the path. But as you see, once the map is generated, once we get over the number 9 here, by the way, we start going into letters, but it counts up 7, 8, 9, A, B, C, and so on. So the goblin is starting on, I think, a K square, and so it's just going to walk down J, I, H, G, F, E, D, right? And so that is one optimal path solution to get to the player. And the neat thing is that once you've calculated this map, you can stick that goblin onto any square in the map and just walk down the numbers, and you'll get to the player every time. And it also works for multiple actors, like I mentioned before. So this is just another simple example showing multiple goblins wanting to navigate to the player, and each one of them can just look at its neighboring squares, find one of the squares with the lowest value, and then move to that square, and all of them now have a path to the player. So we didn't have to calculate this separately for each individual goblin. We calculated it once for the map, and then we're done. And of course, this works as well when you have obstacles in the map. So just like before, this goblin will take this path, this one will take this path, and so on. So one calculation, multiple uses, which is nice. So if you break this down into kind of a turn-based timeline, this is how it looks. First, when the AI is about to plan its move, you generate the map around the target, which again in this case is the player. Each one of the actors takes a look at all of the surrounding squares and finds the lowest number. And in some cases, it might have multiple options because the lowest number occurs multiple times in the 8 squares surrounding it. And then it will choose one of those squares to move to and make the move, right? So I had these goblins. They looked for their path, the lowest number to get to the player, found it, and moved into one of those squares. Now on the player's turn, the player moves to a new square, and once they do that, we recalculate the map because the location of the target has changed. So now the player's moved, your old map is invalid, you throw it out, you generate a new one. But I guess the key point is we didn't have to calculate paths for each of the 4 goblins. We only calculated the path for the player target, the map for the player once. So that potentially can be much more efficient than the A-star solution. Okay, so now we're going to get into more interesting stuff. That was the basics. So let's imagine, as a simple example, we have these goblins who want to get to the player, but they're also greedy and they like money. So scattered around this map, I've placed some dollar signs that you can see surrounded by kind of yellow color coding. And when we generate the map for these greedy goblins, we use not only the player as the goal, but we use the coins, the dollar signs as the goals as well. So Dijkstra maps can be calculated with multiple goals. It doesn't just have to be a single goal. So you can imagine in this example, if you had a goblin somewhere to the right of the player, maybe on the number 8, it would walk down numerically and it would go to the player. But maybe just 2 squares to the right of that, past this threshold, the number 9, now it's actually closer to this coin up here than it is to the player. And so if you were to drop a goblin down there, it would sort of, you could imagine it thinking, should I go for the player or should I go for the money? And it would go for the money. So this is just a really basic way of creating the illusion of some intelligence for your AI characters in your game just by giving them multiple goals. And you can take that one step further and you can assign different priority levels to the different goals when you're generating the map. So in this example, we left the player, the @ symbol, as a goal. So it's still at the number 0. It's standing on top of the number 0, which kind of represents the goal. But we've given the coins more priority. And in this map, if the number is written in gray, that means it's negative. So we've given the coins a target priority of -4. So the more negative the number, the higher priority it is, right? Because you're always walking down the tree to the lowest number. So the lower you make the number, the more the map wants to flow in that direction, right? So we give the coins a very negative number, and we give the player 0. And so now you can see, if I were to place a goblin here, maybe on the number 0 down towards the bottom of the screen, sorry, that's not a great example. Let's say, let's say a little further up by one of these 3s. It's actually physically closer to the player, but it wants that gold so bad, it's actually going to walk down and get the gold before it tries to go back and get the player. So that's an example of assigning different priority levels to different targets on your Dijkstra map. And again, it kind of just creates this illusion of intelligence. There's no real intelligence there, but you get the illusion that these goblins are greedy, and they want to go for the gold first. And so, and of course, every time they pick up a gold coin, you need to regenerate the map, removing that as a target. And you could imagine a scenario where they would go around and get all the gold first before going and then finally attacking the player. Okay, so here's another, we've looked at Dijkstra maps in the context of finding a path to a target, but let's imagine the case where an enemy, shown here by this R, has taken a little bit of damage, and they suddenly decide, you know what, my life is more valuable than this. I'm done. I don't want to fight this player anymore. They want to run away. So the idea is, okay, how do we make this actor flee from the player? Now, probably the first thing that might come to mind is, instead of walking down the numbers to get towards the player, why don't we just walk up numerically? And so using this Dijkstra map that has been generated, targeting the player, I took the numbers off, apologies for that, but you can still hopefully look at the color coding and it'll make sense. You're going to be walking towards kind of the purple colors and away from the yellow colors, if that makes sense, right? So this R down here in the corner of the room Well, if it moves to one of its target squares, highlighted in white here, you can see it's not really going to flee from the player. It has two surrounding squares which have a higher number than the one it's currently on. It's going to go into one of those and it'll just be stuck in the corner indefinitely, which is not working for fleeing mechanic, right? So there's actually a neat little trick to, well, okay, I'm sorry, forgot about this slide, but this is just a simple example of putting some more hypothetical enemies into the room and giving them this fleeing mechanic. And you might get lucky, like the one that's running straight down, and it just happens to be centered above the hallway, and it looks like, oh, wow, that one was smart. It ran down the hallway. But you just kind of got lucky in that case, because most of the other test cases here, the AI will just run into the wall and bump into the wall and not do anything from there. So how to solve this problem? We really want to target the highest number on the map, which is highlighted here by the red circle. So how do we get the AI to flee to that spot? And what you do is you basically use that as a target square and you invert the map. And there's some number fudging required, and I'll just leave that out, but go with me on this. Hand waving, it works, okay? And so you use those as the target squares. So now you see my most yellow squares are the numbers that were the highest numbers on my previous map. That's now the target. That's where we want to go to. And this doesn't quite solve the, oh wait, we inverted it first, sorry, to find the target squares, and then we regenerate using that as a starting point. Sorry. A little bit of math behind there that I'm not going to go into, but Derrick's article on Rogue Basin has an explanation of why you do that and why it's necessary. So, and by regenerating the map using these new target squares in yellow, if you look around the doors, it's a little hard to see. Sorry about that, but in any case, the map kind of flows outward from the doors and goes out into the corners. So if you had a character in the corner, it would intelligently find its way out of the room and into one of the hallways. Sorry about that. Into one of the hallways to get out of the room. So that's kind of a neat trick to, you can see if I had that character back where it was in the original example, it would actually move up to the hallway and out. So now you have your fleeing mechanic. Okay, this is another cool application of Dijkstra maps. Something called, trying to target an optimal range from the player. So if you imagine if you had an enemy that was an archer, and they were weak on kind of hand-to-hand combat, and they wanted to be a certain distance away from the player and kind of take pot shots but not get in too close, what you can do is you can generate the map around the player, and then instead of using that map with 0 where the player is standing as the target, you pick another number. So if I want to be 4 squares away from the player, for example, I take all of the 4s on my map and I turn those into 0s. Those are now my target squares. And I regenerate the map using those as the target. And so now you can see if you're walking down to the lowest number, basically my enemies are going to situate themselves always 4 squares away from the player, but no closer and no further. And then just a little icing on the cake, when you do assign these new goal squares, you can also implement line of sight to the player. So these 0s over on the right side, they're not going to be able to see the player through the wall, so you just cut those out. And then you regenerate it again, and now you've basically got this really pesky archer that is always just a little bit out of range for the player and kind of wreaking havoc. And again, there's no intelligence here. You haven't coded up this crazy big state machine trying to get the AI to pathfind to the best spots to take shots at the player. You just generate the map, and you just have the AI follow the map to get to the optimal spot. Okay, I'm almost done with my examples, then Patrick will take over. This is a pretty cool one. Autoexplore. Was it Angband that had an Autoexplore feature, or which one was it? Oh, DCSS. Okay. So Autoexplore is the concept where you just allow the player to turn on autopilot and have the player move throughout the dungeon until they find something interesting or dangerous. And you can do this very easily with Dijkstra maps. What you basically do is, if you imagine what we can see here over on the left side, that's all of the level or the map that the player has discovered thus far and seen. And then you take every other node on the grid in the map and you turn it into a a goal, right? You give it the number 0. And then the player will automatically move towards the lowest number. So you can imagine the player will move to the right here until they get to the end of the hallway, where they then see some new squares. So now that you see some new squares, you regenerate the map again. You use everything that hasn't been seen by the player as a goal, you regenerate the map. And now the player gets there and they'll walk down the numbers again. And then, so they take one step and they see a new thing, so you regenerate the map again. And then they move down again, they discover more of the map. And basically every time you see a new thing, you're redoing the map generation. And sort of hand wavy, but this is just a really cheap way of implementing Autoexplore. And much in the same vein as Autoexplore, you can do this for cheap mouse pathing. So roguelikes that have a mouse interface, a lot of times if you move the mouse cursor around on the screen, you'd like to generate a path to the mouse cursor to show a highlighted route to get from one point to the other. And so in this case, you just generate the map once around the player, and you sort of pretend that the mouse cursor is an AI, like in our previous examples, and you just walk down the number numerically until you get back to the player, and that generates a path. And it even works for areas that the player hasn't seen yet. Right. Okay, so that's my part of Dijkstra Maps, and Patrick's going to take over with some of his insights and ideas and personal experience.
All right, let me try not to kick these wires. All right, I'm going to hit 3 things. We'll use some of what Brett just talked about to talk about some simple pack behavior that we might want. Then I'll talk about some projects that I've done, and then I'm going to talk about some trouble that I ran into, and I'm not sure if that trouble is real or if I just misunderstood something, so we'll see together. Here's just a basic map. I'm going to use some Jackals as an example. As Brett described, we can use the same generated map to drive multiple agents here. So we've got 2 J's, and you can see in that cyan highlight that they will both path to the @ sign and attack. One problem that I see here, though, is that they're both going to go the same way around the wall. And this will let the player just kind of pillar dance or kite them around and around and around the wall. We would, let's suppose, prefer that the Jackals act in cooperation with each other and flank the player. So how can we accomplish that? I do that by adding some cost to certain cells. This is a function here. Basically, it says, hey, we're going to be able to add a cost to anything that's within a certain radius of some particular target. And then down here at the bottom on the far right, you can see I use this get neighbor cost to say, let's assign a cost of 3 to moving through a cell that's within radius 2 of any jackal. As you'll see in a moment, I didn't actually realize that. Back to Tom's point about the candy machine interface here, I thought that position at distance was inclusive, but it is exclusive, so it actually generates a ring where I was expecting to have kind of a filled-in circle. You'll see that here. So what we get here is you can look at this lower jackal, and you can see that A, B, C, D, E, F, but then we skip to I. So he's got a ring around him where it costs 3 to pass over that ring. And he has no choice but to kind of plan to go out of his own ring. And so it doesn't matter if he's alone. But he really doesn't like the idea of going past his friend here. And so he prefers to actually go around and flank the player. And we get the desired surrounding behavior here. This slide is just to point out that when there's no choice, of course this isn't a prohibition on going near other jackals, just a favoring of staying away from them. So when there's no other choice on the left, they will move together, and even if we punch a hole, but it's just a bit too far of a way to go out of your way around, they'll just go the same way. Now this is revisiting the example you saw before with the archer. I think this is kind of neat, so I just threw these 2 lines of code up here. In the first line, we're creating a Dijkstra map from the physical map. That map variable there is the physical one with like the @ signs and the walls on it. And this first snippet here is defining what our goal is, and that second one is defining what is impassable. This is all Derrick's example and Derrick's code here. So what we do is we make a Dijkstra map that allows us to path towards the @ sign as we've been seeing, but then we create a second Dijkstra map, not based on the physical map, but based on that first approach map. And then we say our goal is not to get to the @ sign, but to get to a number 4 on the approach map. But then note that we still pull from the physical map on the right here what's passable and impassable. And so we've sort of combined the physical map with the distance that we got from the first layer of Dijkstra map. So I think of this as kind of chaining the maps together. The reason I bring that up again is because you can combine these 2 techniques, right? Here we see that the 2 jackals are going to, now these are archer jackals apparently, and they will want to get to the 0. But we can also make them a pack of archer jackals where they will still flank but then maintain their range. And you can tell by the way that they hug the corner tight that this is not Rogue. Okay, so now I'll talk a little about my own experience, which is minimal. I'm not a master at this stuff by any means. I've used it in just 2 projects. One of them was one of my very first projects when I got my hands on Unity, I guess second project really, which was a real-time top-down shooter. And the second one is my 7-day RL for this year. Both have some non-traditional aspects to them, or in the prototype's case, it's not roguelike at all. So this shows that you can use them outside of Berlin. This is a little programmer art on the left. If you can't tell, that sort of like sea green blob over there is the player. And what this is like, call it an action shot, right? What I was doing is I ran into this pack of enemies. I was near the wall down here at the bottom, and I was trying to backpedal as I shot them, which is kind of a recurring problem in these top-down shooters, right? That you can just kind of retreat backwards and shoot everything that comes your way. And I was trying to combine that with kiting them around this large pillar here. But these 2 pesky guys here flanked me because the group was big enough. They didn't want to walk past their friends, so they went around the other way. Couple of things, just points from this experience. I had no problem running this in real time. I was creating several different maps, so I was doing multiple passes at it. This blue beetle thing here really likes to sneak up on you and opens its mouth and charges at you. And so it had like a bit of a different behavior than the others, and running multiple real-time Dijkstra maps was not a problem. I don't think I recomputed them 60 times a second on the frame, right? But it was faster than once a second that I was running these. This game is real time. It has a discrete space when it's doing the map gen that is utilized by the AI, even though the gameplay itself takes place in a continuous space. So you can kind of see these gray dots indicate, the tiles, and clearly there's like a grid-based tiling here, but the locations of the characters are not anchored to cells. But still, they would just run towards the cell that they decided to be into, and so it really worked fine. Although separate attack logic takes over when they're close enough. They're kind of scanning, hey, if the player's in front of me and they're really close, like leap at him or whatever that particular enemy does. This one is a bit more of a questionable fit. This was my 7-day RL this year. It's called Billiard Dungeon, and I was trying to get this feeling of thinking about the way that the end of this turn will leave you for the basis of the beginning of the next turn, right? Because I feel like this is the experience of playing pool. You take the shot and you're trying to accomplish something, but you're also thinking about where is that going to lead me for my next turn. And so you can kind of see here in the screenshot that I'm contemplating a turn that's going to bounce off that pillar, and then and every turn is a pool shot. And this, we were sticking with Jackals here, so this Jackal would then not have a clear line to take a shot at me, right? So this is like the way that I'm thinking about this game. So it's turn-based, but there's these large any-angle shots with variable power, like a billiard shot. It's a continuous space with oddly aligned geometry. This tiling here is purely decorative. There's lots of obstacles and bouncing. And knocking things around, and so maybe it's not a great fit, but halfway through the 1 week time, I needed something, because if I broke line of sight with an enemy, they really wouldn't know what to do about it, and they would not follow me around a corner, and this was a gameplay problem, so I needed some kind of a solution for it, and I wanted to do something I was familiar with. So I kind of square peg, round hole, I got out my hammer, and I started banging. So the first thing I did was I had to convert this continuous space into a discrete space. So I sampled physical space at an interval to create that grid, even though it didn't really exist. And this is a little snippet of the Unity editor where I've exposed a couple of variables here. I can set the size of this sampling rate, and I can say a few things about what constitutes impassable terrain. And you can see here, I've simulated the sampling with these dots, and they're red where it's impassable, and they're yellow where they are passable. We see this one intersects with the player, and so that's now we're able to move into the space where we can apply a Dijkstra map. And the goal on that Dijkstra map was gain line of sight to the player, because the monsters were really fine when they had line of sight. It was just when you sort of broke that by sneaking around a corner that you could lose them, and I didn't like that. Now, one thing is that a Dijkstra map kind of assumes that you're stepping cell by cell. Right? That's sort of the fundamental assertion of the whole thing, which is totally untrue in this game. So I had to get the way that the enemy would decide how to use that Dijkstra map when picking its turn is that it would just generate a bunch of candidate moves, right? So first of all, if we have an attack, we take it. But otherwise, we consult the Dijkstra map, and we generate some candidate moves. Here, I've shown a few, but in reality, it was more like 20. And then we take a guess at where those are going to end up by taking into account the fact that we're going to bounce off that wall in a very primitive way. We reject any moves that intersect with hazards, so there's a lot of traps in this game, and finessing around spike traps is a dominant theme, let's say, sort of more than I intended. So this approach does okay. It struggles, and so I thought I would include this little video here, and we can kind of see it in action. But let me tell you what's gonna happen, so you can know what to watch out for. I'm gonna be dancing around with this Jackal here, and he's gonna start by coming up to the right, because before this clip begins, I saw him by poking my head out, and then I retreated around the corner, so I broke line of sight. Now he's gonna attempt to pursue me, but he's gonna struggle a little getting around the corner, and then these things here are spike traps. And so he's going to struggle to get to me because of the spike traps. And you'll see he's pretty awkward, but ultimately I'm not able to just escape him by breaking line of sight. So for the purposes that I had, I think it gets the job done, although it's not exactly pretty. So here he's kind of thrashing around. The only moves he consider are full force all the time. So that's a lot of the reason that he struggles getting around that corner. Oh, we have sound. I didn't realize that was coming. But then as soon as he's able to develop line of sight on me, you can see that he's able to get some hits on me. So that's just a quick slice of how that all worked out. Whoop, thanks. Okay, so would I use them again? In that top-down shooter, I would say sure. It worked fine in real time, and I find it really compelling, the variety of behavior that you could explore, creating all different kinds of enemies and mixing these things together in different ways. For the billiard game, I'm not so sure. I don't really know what the right approach there would be. That many-celled movement was just fundamentally at odds with the approach. So I would say that the result was okay. It got the job done in the short time allowed, but it didn't shine. Okay, the last thing I'm going to talk about here is this idea of weighted sum maps. So this was one of the most appealing ideas to me in this article, and also the Roguelike radio interview with Pender, who made Brogue. And he talks about this idea of having multiple different desires, each of which is represented by a Dijkstra map, and then having a coefficient or a weighting for each of those desires, and then just doing basically a weighted sum of those different maps. And then he says, with 9 weighted sums, you would have a monster intelligently weighing conflicted ideas. And then he gives this fabulous story about this complex thought process involving water and running from the player and getting together with your friends and all these different things. And strangely, this was maybe what got me interested in the idea originally, although when I actually got to the point of implementing this, I ran into some problems, which I'm about to hit. But before I say that this doesn't work, that's not really what I'm saying. I'm saying when I tried it, it didn't work right away. So if you can see what's wrong with it, I'm all ears. I might have just been being stupid here. That's totally possible. So we're going to return to our Jackals, and this time we're going to say that they want to steal food. Let's ignore how totally OP that would be, and say that it's okay. We're going to have that be the way Jackals work. So we want a Jackal to be willing to go a bit out of its way for some food. It primarily wants to attack, but it should take a little detour if that's available. But it should not go halfway across the dungeon and hunt food, essentially. It should really hunt the player and opportunistically grab food. So I've created this little scenario where the Jackal wants to get to the @ sign, but there's a piece of food. As you see on the left, it wants to hug the corner, but if it just goes one step out of its way, it's going to be able to pick up a piece of food. I think it's reasonable for it to want to grab that food. So let's see what happens when we just combine those two maps with even weighting. You can see in the top here that actually the cyan path just terminates. It doesn't get to either goal. It arrives at that corner, and then it's like, hey, one step closer to the food, one step closer to the player. I'm totally indifferent. And it just sits there. And what's particularly frightening about that is this bottom picture. This is regardless of the distance, right? Anywhere in this field, moving in either direction is like one step closer to the player, but one step closer to the further from the food. So, why bother? And it creates this gigantic sea of indifference, right, where nothing can happen in there. So even weighting is dangerous. Watch out for this, I guess, if you use these maps. So we're going to unevenly weight them, obviously. If I make the food slightly less valuable than the attack, I just go for the attack in both cases, right? When I get to the border of that indifference, I'm no longer indifferent. I'm decisive. I want to attack a little bit more than I want the food. So it's always a bit more valuable to go and attack. If I favor the food, at first it looks like, hey, maybe it's okay because I'm going to grab that piece of food on my way. But I'm also, as we see on the bottom right here, going to wander a mile out of my way to go for it. Did I get it wrong? Okay. I look forward to that explanation. So it seemed to dominate, right? And I have some kind of kludgy solution that involves creating a tie break on purpose, right? Because what we can see is that you're only going to favor the lesser weighting can only break a tie from the point of view of the more dominant weighting. And so here what I did is I used our neighbor cost again, but I said it's free to move near food. Within one cell of food is free. So the attack one is indifferent there to how it's going to move when it encounters the food. And then this map will break the tie. Whereas on the right, when the food is far away, we're not indifferent. We move in and we attack. So this was like a hack putting it together. So that is all I've got. But I'm totally happy to hear what I've overlooked here, because I'd love to unlock this in a meaningful way.
I like that. So when I use something like this in the strategy single-player game where you have lots of armies battling and stuff, I was building the campaign for an existing multiplayer strategy, and it was tile-based, turn-based. really constrained processing bar. But the point was the troops were deciding where to go by themselves. And it's funny, I had never, at the time I didn't correlate it to Dijkstra, but of course it is. But I thought of it as heat maps or value maps. And so it's like clerics like being close to people who are getting hurt. And archers like being close to enemy flyers. And flyers hate being close to enemy archers. And that sort of thing. So then I would weight sum the whole thing and multiply, etc. Now the key difference there, in my opinion, what I think you could have done here to help it is, if you think about it as a value map, can you go back one slide, please?
Yes.
So if you think about it as a value map,
Okay. Hi. So sorry. If you think about it as a value map, you're telling me that I think it's one before. Was it one before? What's the one where? Yeah, this one. So see, you're saying here that let's say being here is like double or double the value of being here or something, and being here double is a weird number to be used. I shouldn't be using numbers. But my point is, being at the food is a lot more valuable than being near the food. So when you move one step closer to the food, hey, that's good. You're making progress. But the moment you step on the food, it's a lot better. And the moment you're within range to attack the player, it's a lot better. So if you make these have drop-offs that are not linear, then you get these interesting peaks, and it solves the problem partly because as they're walking by, they're like, well, I'm kind of near the food, so I could grab it. But then it becomes, you know what, I'm moving to attack. Oh, I can totally make it to that piece of food. And then they stop what they're doing and they go get the food, and then they go attack the player. At least that's one way that I solved it, if I remember correctly. It was like 8 years ago.
Makes a lot of sense with the nonlinear, right? Because there's sort of an assumption here that this is counting how many steps away I am.
Yeah, that's
But if you break that, if you throw, there's not a lot of value in that, right? It's just what's the best square to move toward.
So I used floating point numbers, and it was so much tuning. In the end, I built an artificial evolution system to figure out the best balance.
Really?
Yeah.
And how did you visualize it all in the debugger?
Oh, yeah. And when you're running the game, if you hit certain keys, it would show the heat maps and the numbers, and pretty much like this, red to green, whatever. And so it was heat maps, so you could see what the archers were thinking and how they were failing to go around the mountains or whatever. And then I would leave it running overnight with different sets of parameters for the values that I tweaked manually, of course. And then they would kind of iterate on it, and the AI would battle each other. And they would find the values that work better.
Until you had the fiercest archers you could get.
Sorry?
Until you had the best archers you could get.
Yes.
When fights, yeah.
But it was still like a huge, the fact that I got to that length shows you it was a huge work of tweaking numbers.
Yeah.
It's so hard to compare, I want to be near my enemies, but not alone. So, but how much one way or the other? And that makes or breaks the game. It's tuning.
Yeah, and I guess I should point out that, counter to all of this being useful is the idea that, if it gets so complex that you're doing that level of stuff yourself as a developer, then the player won't know how to predict the enemy that well. And so sometimes you shouldn't be doing things like this. You should just have it be really gamey, like, hey, it's like a chess move. Like, I know what that guy does. Right, yes, exactly.
Anyway, but I was having so much fun as a developer, so.
So thanks, I like that, the non-linear approach. That's good.
So you've covered the applications of Dijkstra Maps to Pathfinding, but since we're all prop gen wonks here, I actually use Dijkstra Maps in very non-pathfinding ways in Caves of Cud for procedural generation. Because you can think about these maps cellularly. So if you know what a Voyer-Arni diagram is, they're similar, but they respect geometry. So for instance, let's say you have an uneven play field with some blockages, right? Some hills and trees, and you want to place a cluster of tents. This is actually like a very non-trivial problem. I want to lay out like 6 rectangles in a way that respects geometry.
Yeah.
And in Caves of Cud, I will do things like drop a bunch of targets, Dijkstra Map targets, into the terrain. I want like 8 of them, or I'll drop them until the regions that they generate reach a threshold of size, and then I will say, okay, well, these have respected distance from terrain and float around them, and now I can just pluck the 6 largest rectangles that have been generated and plop a tent down. Another application in caves have cut is, let's say I've dropped these Dijkstra cells down. You can imagine them colored by the closest seed that they're attached to. You can then generate a graph from their relationships from touching. And you can say, well, I've generated these caves with a cellular automata process, right? And it's very random. I need to do train analysis. And so what I do is I drop a bunch of seeds until you've got cells that are maybe 40 cells total. And I will draw a graph where the cells touch each other. And then you can actually say, oh, well, this one only touches one other cell, so it's a dead end. That might be a good place for a treasure room or a boss encounter. And so they have a lot of very interesting applications. Another one is, for instance, in the sound system. I'll use Dijkstra maps to do the volume attenuation around corners. Right? And so there's an awful lot you can do with this very straightforward tool that doesn't have anything to do with pathfinding. Pathfinding is one great application, but definitely think of it in terms of terrain respecting analysis, and you suddenly see this whole world of other applications.
Interesting.
Cool.
Yeah, I mean, more examples of that. You place a city, Dijkstra map from there, then that is a probability density of where other cities can go, so that they're not going to accidentally be two cities right next to each other.
Okay, yeah.
Each city you can regenerate, so they keep trying to get cool areas, or just drop random river sources and let them flow downhill, and so they'll merge into major rivers.
Cool.
Let's take one or two more and then move on.
Okay.
We are running a little behind, so.
So is it correct to understand this as kind of almost a discrete specification of gradient descent? Because this is what the gradient descent looks like.
Yeah.
Okay, so and then my follow-up question to that would be like, how do you keep from getting stuck in a local minimum?
So you regenerate the map once you hit a minimum.
What's that?
You regenerate the map once you've hit one minimum. Then
Right, okay,
regenerate
but
the map, taking
but
out that
But you
target.
can easily, all I'm saying is that you can easily imagine a situation where, for example, maybe things are static, and you maybe as long as the player is in a particular area, even regenerating the map might keep the monster keeps trying to go through a corner or something like that. Sure.
I don't think you can get stuck in a local minimum like that. I think you can kind of think of it as starting from the goal and then just sort of radiating outward with a step away from the goal. That's one step away, 2, 3, and so as long as you're rolling downhill, you're always rolling not towards the location, but along a path that will get you there. If that makes sense.
What you're seeing is a breadth first graph, and as long as you're traversing towards the route where that breadth first started, there's always a walk close.
Right.
So what they showed is when you go the other way, you can hit local minima, and so it's very unintuitive to your monkey brain what's going on. But
This actually might be a good just example of that. There are so many paths here that are the best path, right?
Yeah.
But there are no local minima, and I just plop down walls, right?
What happens for the G? The path isn't necessarily optimal.
it is.
Okay, so the G can move.
The G can move to either of those areas.
So
Yeah.
any of these J's are just as valid as the other ones. So I think the path that I did something like this, but I could just as easily go, J, I, H, G, and then around this way. It's as long as you're always stepping down one letter.
Did you do this manually, this line?
This was generated.
Because I think the one above you, the goblin with the K, is part of the point.
The goblin is standing on a K.
No, the one above him.
The reason why that is because it's breadth first, and that's why you can't go the other direction. It actually is directional.
Because you can go around the corner.
Yeah, it's stuck.
One last thing and then we can have more discussion about this.
You got your hand up.
This is actually to Tom. Tom, you worked on The Sims. Does The Sims use something like that for the various needs?
No. Sims uses A-star for individual unit pathing.
Okay.
The various needs are at a more abstract level. You've got a toilet and an oven in the same room, and they broadcast what they're willing to provide the little
I see. So not geometrically,
And
but
then the little,
abstract.
and then the little dude chooses, but then it goes through 2 stages of abstraction of that. The little dude basically sorts all the things that might give him something, and then randomly picks the top 4, but also looks at the little dude's 6 need values,
through a curve filter. So yeah, so you don't have a linear. I'm 50% of the way through my ladder, therefore I have 50% drag. So I'm sorry, that was long, but yeah, it does not actually lose any of it.
Okay, you want to call it?
Yeah.
Okay. All right, thanks everyone.
Thank you both so much for that. I believe it's Sheridan, you're up next with surprises. Do you need me to pull up anything up here, or?
I do have a flash drive loaded with a couple video files and some images.
Oh, okay.
Is there any chance that I could hook this laptop up, possibly? Because it looks like you got kind of a complicated setup here, and if it's
Yeah.
swapping a few cables, then we'll say no.
It is a little it is swapping a few cables in terms of in person. The problem is the stream.
Yeah, it looks like you got OBS running here. So
Yeah.
I'm sorry about that.
So actually, no. We're going to take a short break. I'm going to set this up in the back and webcam you.
Okay.
And you can just set up here.
All right.
All right?
Can I get everything on the projector?
Yes.
Okay.
So we'll be back. Always an adventure.